integration and Riemann analysis class. So today we'll check why Riemann integral is not good enough for us to find the area under our function, and then this will be a motivation of why we have to look for a better theory to remedy some problems we are going to list out in this session 1b. So the Riemann integral works well enough to be taught to millions of students of calculus around the world each year. However, there are some limitations to Riemann integral, and then we are going to discuss 3 issues that Riemann integral will not able to achieve, and then that will be a good motivation for us to start under theory in session 2a. Alright, the first 3 issues. Let's see. So we have the first issue is, let's take 3 issues. That's Riemann integral Riemann integration does not handle so the first one, Riemann integration does not handle functions with many discontinuities. So let's give an example of that. Example, a function that is not Riemann integrable. So define f 0,1 to r. So we have f of x equals to 1 if x is rational, and then 0 if f is irrational. So for this, if we define any partition, so define any partition P okay, and for any sub-interval we picked, particularly for x naught, which is equals to 0, common x1. So at this point you will notice that the soup of our function, or for any sub-interval we pick, the soup of our function over this will always be 1, because rational number, because any point we pick always contain irrational number and also rational number. So the soup of the function over any sub-interval is 0, 1 will always be 1, and the infimum f of any subinterval will always be 0. So let's make this for x j minus 1. So let's make it for any j's. For any subinterval we pick, sub f will always be 1, and then the infimum will always be 0. So that means that the upper Riemann sum will always be 1, and then the lower Riemann sum will always be 0, and then the upper Riemann integral will always be 1, and this is not be equals to the lower Riemann sum, which is 0. So that means that f is not Riemann integrable. However, in the later on, we know that this function 0, 1 contain a far fewer rational numbers than irrational numbers, and then these functions at most supposed to have the integration of this function supposed to be 0. Why? Because the later on we are going to see that the measure of rational number should be 0, and since function is already 0 in a rational number, then the upper Riemann sum and the lower Riemann sum, then if we make use of another integral example like the Beck integration, then we are going to realize that this function should have an integral of 0, which we are going to check later on. So the functions with many discontinuities cannot be handled with Riemann integration, because of Riemann integration makes use of the supremum and then the infimum of the functions, and we divide the partitions. We usually find a rational number and irrational number, since these guys are dense in R. So another issue, the second issue that Riemann integration cannot handle is Riemann integration does not work with unbounded functions. So example for this, so define f over 0, 1 r where f of x equals to 1 over root x, 0 less than x not less than 1, and then 0 if s equals to 0. So for this also, if you define any partition, forget the first partition is 0 be equals to x naught x1 xn which should be 1, that will be equals to p. So if you pick the first partition, the sub over the first partition x naught common x will be infinity, that is unbounded. Okay, because the upper Riemann sum of this guy will be infinity, and then there's not any how you can control the lower Riemann. So if you check the graph of this, we have something like at 0 here. So we have our graph going to infinity, at this very point. Then from a little bit away from our 0, then we have our graph going this way. Cut on my graph, so that is what we have. So because the function is not bounded as x tends to 0, so Riemann integral cannot handle that. But we know by using improper integral, if we can integrate this guy, integral f 1 over root x, where we take as t tends as, we can make this to be t as t tends to 0. So we have t to 1, because the function is not integrable. It's not finite at t equals to at 0, so we can make use of improper integral and then integrate this. We have 2 root x, then we have limit t tends to 0, then we have t1, then we have 2 minus 2 root t, and that applying the limit, that will be equals to 2. So this should be able to be handled by improper integral, but by Riemann integration we see that this cannot be well handled, and that is part of the deficiency of Riemann integration. Okay, so another issue is number 3. Riemann integration does not work well with pointwise limits. So let's take some example for that. Example, you have let R1, R2 that be a sequence that includes each rational number in 0, 1 exactly once. Okay, and that includes no other numbers. So for k, the positive integer, we defined fk sequence of function of 0, 1 tends to r by fk of x equals to 1 if x belongs to r1 rk and 0 otherwise. So you will see that this So so here each of fk is Riemann integrable. And then integral is 0 to 1 of fk will be equals to 0. Okay, the reason is because if we define partition and the subinterval contain n of this our RK, the soup will be 1. Okay, but it's only contains just as a single point, and the length of a single point is 0, so it do not have no contribution. That means that the upper sum will be 0, and then the lower sum, the infimum of this, will always be 0, either it contains this point or not. And if it contains this point, the infimum will still be 0. So see that we can approximate our upper Riemann sum and lower Riemann sums to be equals to each other, and that shows that for each case fk of x is Riemann integrable. So we can now define the pointwise limit for large k. So defined f, which is the pointwise limit function for our k, by f of x equals to 1 if x is rational and 0 if f is irrational. And we already showed this one that this is not, and this is not Riemann integrable. So the sequence of the function is Riemann integrable, but the pointwise limit function is not Riemann integrable. Okay, even though that f of s is a pointwise limit of the sequence of integrable function, but then by 1, and yet since that this is not integrable. So those are the 3 simple cases. You can check also. But we have a definition yet to take note. So here we have interchanging Riemann integral and limit. So suppose a comma b and m belongs to R with a less than b, and suppose we have a sequence of function. It's a sequence of Riemann integrables function on a comma b such that the function is bounded for all positive integer. So and all x that belongs to a comma b. So suppose the limit exists. Suppose limit k tends to infinity of fk of x exists for each k. So for each x that belongs to a comma b. So we can then define the pointwise limit function. So define f such that a comma b to R by f of x equals to limit this tends to infinity fk of x. So if f is Riemann integrable, and if f is Riemann integrable on a comma b, then integral ab f will be equals to limit k tends to infinity integral h to b fk. So that theorem should, however, the result above suffers from two problems, and the first problem is undesirable hypothesis that the limit function f is Riemann integrable. So if f is Riemann integrable, so your f, that is the pointwise limit functions, have to be Riemann integrable, and the sequence of functions have to be Riemann integrable. So this result above suffers two problems, and the first is that the pointwise limit functions have to be Riemann integrable. So ideally, however, this should have followed from the hypothesis already given, but that is not the case. And if we check the last example we did, we see that it is not always the case. The pointwise limit function of sequence of Riemann integrable function may not necessarily be Riemann integrable. Alright, so we stop here for section 1b, and then in the next video we will try to check some selected solutions to exercises 1b. Then we move to the main measures, which is the main focus of this playlist. Thank you for watching. Don't forget to subscribe and share with fellow grad students mathematics. See you in the next video.